Hi, and welcome to this quick recording for problems from chapter 44 as promised. So the problems I'm looking at right now are problems 41, that's on page 1523, problem 42 and problem 43 potentially, so those are the three problems. And we're going to also do problem 44, 48, that's problem 48. It's a little bit harder than the other two problems. The other three problems, potentially also problem 49. So we have quite a few problems in here to discuss, maybe even problem 50. So you will see that I have actually the book open right now. You will see that we will need, as we said in the lecture, table 44.3, okay? And the table you are going to need is on page 1496. So that's something that you will need. Some of the problems actually will require the table before it, 44.2. So that deals with the leptons. Leptons do not engage in strong nuclear reactions. Therefore, probably we're not going to be doing a lot of those things in here. Anyway, so let's do problem 44, 41. That's problem 41. So problem 41 is, it says each of the following reactions is missing a single particle. Calculate the baryon number, charge, strangeness, and the three lepton numbers, where appropriate, of the missing particle, and from this identify the particle. So basically we have 1, 2, 3, 4 basically reactions, and we want to find the missing particle. So the first one is, you have a proton and a proton not neutron, giving you a proton plus a lambda particle of charge 0. Okay, so we want to find the change in the baryon number. If you look again at the table 44.3, it will tell you all the information you need. For a proton, it has a baryon number of 1, positive 1. The other proton also is positive 1, and this proton also is 1. So in this case, how about the lambda particle? If you look at it also, it shows you on the column that says baryon number, that too has a baryon number of positive 1. So all of this then indicate that there is no change in the baryon number. So we know this particle in here that is unknown has a baryon number of 0, because without it there is conservation of baryon numbers in here. Okay, so the next one we're supposed to check is the charge. Okay, this one is a positive E, this one is a positive E, this one is a positive E, and this is a 0 charge as indicated by the number in there. So the charge actually here needs to be a positive E. So the Q must be a positive E. Okay, so it has to be positively charged. Okay, what's the third thing in here? The strangeness. If you look at the strangeness S for this reaction, and look at the table in there, for the proton it has 0 strangeness, and for the lambda particle it has a negative 1. So this proton is 0, this one is 0, this one is 0, this is a negative 1. So the S for this particle must be equal to positive 1 to compensate for that one, so that there is no change in the strangeness. Okay, conservation of strangeness. So we have everything now. So we know this particle must be how about the leptons? It says that the leptons, when applicable, none of these particles are leptons. All of these are actually baryons. So all of the leptons are 0. Okay, they're not applicable in this case because it says whenever it's applicable. So we know this particle cannot have a lepton number, because if it does, it's 0. Because anyway, we started with no leptons and we ended up with no leptons. So if we look at the table now, and we're looking for a particle that has a baryon number 0. So it cannot be, it cannot be really a baryon, it has to be a meson. Okay, so that narrows the search in here. It has to be positively charged, so in this case it's either a pion plus or it's a cation plus, and those are the only two options. Okay, both of them have a or it could be actually an antiparticle for the pion minus or the cation minus. So let's look at the the baryon number is 0 for all of the mesons. The charge is positive E, and then the strangeness must be positive 1. And if you look at the choices that you have in this case, the only particle that fits the bill is a cation plus. So this particle is actually a cation plus, positive cation. Its baryon number is 0, its charge is positive E, and its strangeness, if you look at it in the table, it's exactly positive 1. So that is the only particle on that table that fits the bill. So that's the missing particle in here. Okay, now we're going to do the same thing for the rest of the reactions so that you can see that this is just following the same prescription. So let's look at the reaction B. So what we have in this case, you have a cation minus plus a neutron giving you a lambda positive plus something that we don't know. So let's check the B first. Okay, the baryon number for a cation minus is 0 because it's a meson. Okay, so this is 0. The baryon number of a neutron is 1, which is actually a baryon, positive one that is. And the lambda 0 is actually a baryon also of baryon number 1. So this particle in here must have a B is equal to 0. Okay. Now, in terms of the charge, Q. So this is minus E. Okay. This is 0. This is 0. So the charge must be equal to minus E also. Okay. So that at the end we have conservation of charge. Now let's look at the strangeness. The S for the chi minus is actually negative 1. For the proton, for the neutron, just like the proton, is 0. For the lambda particle, the strangeness is 0. So in this case, S for this particle must be exactly 0. So we're looking for a meson whose charge is negative E and a strangeness of 0. Of course, the leptons there are no leptons in here. So this, if we look at the table in here, the only particle that fits the bill actually that has an S equals to 0, baryon number that is 0, and a charge that is negative 1, negative Q, is actually a pion with a negative charge. So that is the particle that's missing. I'll leave it to you guys to finish the other two reactions. The next one is actually proton plus an antiproton. You have to be careful. Let's do that, okay? Because with the antiproton, the baryon number is actually not, it has to be the negative of what is listed there. So we have a proton plus an antiproton yields a neutron plus something, okay? So first of all, the baryon number. This is positive 1. This is actually negative 1, and this is positive 1. So the baryon number must be equal to negative 1, okay? For this particle, the one that we're looking for, the mystery particle. The charge Q. This is positive 1, this is negative 1, this is 0. So the Q now must be equal to 0. And then let's look at the S, the strangeness. This is 0, this is 0, this is 0. So S must be equal to 0. The leptons are again, because we don't have any at this point, so we're not worried about them. So if we look at this particle from the tables, first of all, the baryon number is a negative 1. And all of the baryons that are listed in there are exactly 1. So that means this is an antiparticle. It cannot be a particle in there. okay, because of the baryon number. So we know it cannot be that. The strangeness also is 0, and there are only 4 candidates for the strangeness that are 0, either a proton or a neutron or a delta plus plus or a lambda plus of type C charm. Then in this case, so that's basically the options that you have, but the charge is equal to 0 actually. And if you look at the charge equal to 0, the only one that actually has a charge equal to 0 and also strangeness equal to 0 is a neutron. But this is not any neutron. This is actually an anti-neutron because of this number. So this is an anti-neutron. That means it's an N bar. Okay? So that's it. That answers the question. So you can work with the next number. You have a mu neutrino, antineutrino, plus proton, plus a neutron. Gives you a neutron plus a. Now, if you look at the numbers in here, you have leptons for the last reaction. Okay, so I'm going to leave it to you. So the table that you're going to be using is actually also includes table 44.2, because if you look at the first of all, that's reaction B. So basically what you have in there is you have an anti-mu mu1 neutrino plus a proton, give you a neutron plus something that you don't know. Okay, so let's be careful in here. So what we have in here, first of all, for baryon number is 0, because this has no baryon number. This is 1 and this is 1. So this particle cannot have a baryon number, so B is equal to 0. Okay, let's look at the charge now, Q. The neutrino, if you look at the page, so in terms of the charge, hold on, because it's an anti-particle, so one have to be careful in here with anti-particles. What are we talking about? The charge is 0 in this case for the neutrino. So plus the proton is positive. So this has a plus E. This one is 0. So Q must be equal to plus E. Okay. Now the strangeness. This is 0 throughout, so and that's 0, so it must be 0 at the end of the day. Okay. Now here is the lepton numbers. Of course, we don't have any electron neutrinos or tau neutrinos, so the only one that we have in this case is L mu. So because we started with an anti-particle, this was a -1. So in this case, whatever this particle is, this has no lepton numbers. So the L mu in this case must be equal to -1. Okay. So all of the other lepton numbers are 0. So if we look at the baryon number is 0, so it's either a meson or a lepton. But because it has a lepton number, therefore it must be actually a lepton. And the strangeness is 0. The charge is positive E. So if we look at the L mu in this case must be -1. So it cannot be a mu1, it has to be an anti-mu1, or antiparticle basically for the mu1 negative, because the charge now is positive E, so it has to be a mu plus. So that's the particle that you're looking at. Okay, let's look at this one. So this is actually the anti-mu1. Anti-mu1. Okay, so basically what it has in here, the mu1 has a negative charge by itself, so this one actually has a positive charge because it's the anti-mu1. The strangeness is 0 for all the leptons, so we don't worry about that. The L mu for a regular mu1 is actually a positive one, and this is actually a negative one, indicating that it's an antiparticle. And the baryon number is 0 because it's actually a lepton. So that's the particle that is in there. So that's the entire problem that we did in here, problem 41. It requires some thinking, guys, and when you're doing this problem you have to be careful. This kind of problems you have to be careful. Let's look at problem 42. So all of this is just looking at the tables and deciding which one fits the bill, has all the conditions for all the basically the particle numbers in there. Anyway, so it says in here an eta 0 meson at rest decays into 3 pi mesons. What are the allowed combination of pi 0, pion 0, pion plus, or pion negative as decay products? Find the total kinetic energy for the pi mesons. Okay, so in this situation, so what we have in here is we have a so we start with a 0 charge. That's what we have. So we need to end up with 0 charge. So what are the possibilities of getting a 0 charge? Either having 3, because they said that it decays into 3. So either 3 pions that are neutral, or 1 neutral, 1 positive, and 1 negative. So if you add up all of the charges, the charge numbers are conserved, everything else is conserved, so we don't have to worry about any of the problems in here. Find the total kinetic energy of the pi mesons. So basically what we need to do is, in this case, is subtract the energy for the pi particles, okay, from that of the eta particles. So if we look at the table again, let me look at the table in here, let me find it. So the mass of the eta particle in this case is 547.9. So this is the starting mass, 547.9. And the 3 pions, first of all, if it's 3 of pi naught, so it's 3 times 135 exactly. So if you do the math, this is the kinetic energy, the first one, for this possibility. So let me get the calculator quickly in here. Do I have my calculator? Oops, let me get it in here. So what I have in this case, I have 547.9 minus 3 times 135. So this is 142.9 mega electron volt. Or the second possibility is a little bit different. So this is possibility 1. The second possibility is that it's 547.9 minus 135 minus 2 times. If you look at the table in there again, it gives you 139.6 for the other 2 particles. They have the same mass, 139.6. So if I plug in these numbers, the difference is going to be minus 2 times 139.6. So the answer is slightly less, which is 133.7 mega electron volt. Okay, so that answers this problem. Problem 44 for 43, I'm sorry. Problem 43, it says that the phi meson has a mass of 1019.4 mega electron volt per, that's basically the mass. And measured the energy width of 4.4 mega electron volt per, the units for the mass is divided by speed of light squared. Using the uncertainty principle, estimate the lifetime of the phi meson. Okay, the uncertainty principle in here says basically that the product of the energy and the time must be greater than or equal to h bar over 2. Okay. So actually the order of magnitude is h bar over 2. So delta E times delta T is h bar over 2. So from here we're going to get the time, the life for this particle is going to be h bar over 2 times delta E. And h bar is 10 to the negative 34. I know it's 6.626 divided by 2 pi, okay, times 10 to the negative 34, divided by 2 times delta E. And delta E is given in here. We have to be careful now because it's given in mega electron volt, so we have to convert the mega electron volt to joules if we want to find the answer in seconds. So again, where is the problem? 4.4 mega, that's 10 to the negative 6, 10 to positive 6, I'm sorry, times 1 electron volt is 1.6 times 10 to the negative 19 joules. So now we're going to get the answer in seconds. Okay, so let me write the expression here. 6.626 10 to the negative 34. Oops, what did I do? Okay, divided by open parentheses 2 times 4.4 times 10 to the power 6. I know, I'm saying why don't I make it easy and multiply by, okay, 1.602 10 to the power negative 19. Yeah, 6 and 19 is actually negative 13. So the answer is 4.7 10 to the negative 22 seconds. That's extremely short life. That is because the energy is that much big, okay? In this case, the uncertainty and the energy. Anyway, so this is problems 41, 42, and 43. Problem 48 is a little bit more work, so let's do that and at least talk about the other problems and how to handle them. So problem 48, how much time we're doing now? Okay, 48. Problem 48 says a chi minus particle, so it's writing chi minus is kind of a, I'm going to write it the standard way. I know that's, it should be capital chi. And I'm going to write it like this, okay? Lowercase chi. So it's a chi minus particle because we're going to be carrying a lot of these symbols when you're writing it. At rest, decays into a lambda naught and pi minus. So you have a chi that was at rest, automatically goes into this two particles, okay? So it did not have any momentum to start with, did not have any kinetic energy to start with. Find, they tell you it was at rest, find the total kinetic energy of the decay products. Okay, so the total kinetic energy should be just the difference in mass between the starting particle and the ending particles. That's it. So that's the change in kinetic energy. So the kinetic energy in this case must be the mass of the chi particle, c squared, minus the mass of the lambda particle. I know it has to be this specific lambda, not any other one. C squared, minus the mass of the pi, and it has to be this pi particle squared. So if I plug in the numbers, if I look again at table 44.3, you have to be careful in here. Make sure you pick up the correct values in here, because we started with the chi negative in here. So I have to look at the chi negative in the table, and the mass for that is 1322 MeV. this mass of the lambda particle is 1116 MeV. Okay, and the mass of the pi, and it has to be this pi, which is the pi negative, 139.6 minus 139.6. So this is going to be in mega electron volt, the energy. So it's going to be 1322 minus 1116 minus 139.6. So the total kinetic energy should be 66.4 mega electron volt. So that is the kinetic energy. Because the particle was at rest, and all of a sudden it decayed into two particles. Now the two particles must carry with them combined that much kinetic energy. What fraction of the energy is carried by each particle? Now I have to calculate each particle. Okay, in terms of momentum conservation and energy conservation. Momentum. So initially we had no momentum. At the end, as a vector actually, momentum for the lambda particle and that of the, so it has to be a vectors actually, and that of the pi particles must equal to 0. In magnitude, both of them are equal. Okay? One of them is going one way, the other one is going the other way. So think about it, that you have a particle, a chi particle, sitting still, and all of them is split into two particles. One of them it goes left, the other one must go right. This is conservation of momentum, really. Now we have to find the kinetic energy for each and every one of them. For that, and they tell you, use a relativistic expression for momentum and energy. Okay, so for that, the kinetic energy, the energy of the particle pi. So I have to really, first of all, the initial energy is simply that of the chi particle, and that is equal to m chi c squared. Okay, the final energy now, so this must be equal to the sum of the two energies, the sum of the energy for the lambda particle plus the energy for the pi particle, because there is no more energy from the other one. However, the energy for the lambda particle is given by this expression, the mass of the lambda particle c squared plus the pi, I mean the momentum for that particle, but the momenta are the same, so we can just write either one of them. Okay, and the momentum and the energy for the pi particle is going to be square root of m pi plus p, again pi, and that's by conservation is the same quantity as the other one. So if we plug into that expression, now we have an expression for everything. So let's write it down now. So we have the m chi c squared is equal to square root of m lambda. I have to be careful in here which lambda and all of this number, especially the pi's. You have to be very careful with them, because you have to refer back to the table and make sure you refer back to the problem which pi particle you're talking about, because they have different masses. So again, I have m pi squared c to the power 4, and I have p pi, and this I know from conservation of momentum to be the same. Move one term to the other side, and we're going to be able to find the solution for that number. So make sure I have no so let's do that. So we have m chi c squared minus square root of m lambda squared c to the power 4 plus p pi squared c squared p pi or p lambda. It's the same thing, okay? Equals to square root of m pi squared c to the power 4 plus p pi squared c to the power squared. Okay, if I square both sides, on one side I will have m lambda squared c to the power 4 plus p pi squared c to the power squared, and in here I will have m chi c to the power 4 plus square of this number, which is m lambda squared c squared plus p lambda squared c squared. Now I have to cancel this term already right away because I know that they're equal, because the momenta are equal, minus 2 times m chi c squared, and this quantity is actually the energy of the lambda particle. Okay, the total energy of the lambda particle. So this is E lambda. E lambda. After I find E lambda, I subtract from it the rest mass of the lambda particle, and then I have the kinetic energy. So that's basically in a nutshell what we're doing right now. So for that, I'm going to move this term to this side, and I'm going to move this one to the other side, changing signs correctly. So what I will have is, I will have E lambda equals to, dividing by this quantity in here, 2m chi c squared. I know you're eager to change to cancel the c squared. Don't, okay? Because you have the energies or the masses expressed in terms of energy, so you really don't need to cancel anything. Leave them as they are. M chi squared c to the power 4 plus this quantity, which is m lambda actually squared c squared. C squared? No, that's c to the power 4, I'm sorry. So this is c to the power 4. Okay. Minus this quantity in here, which is m pi squared c to the power 4. And the whole thing is divided by that. Make sure that this step is correct, okay? So this is the kinetic energy. I mean, this is the total energy for the lambda particle. For me to find the kinetic energy, I have to, for the lambda particle, I have to subtract from this number the rest mass, which is m lambda c squared. So this whole thing is going to be, at this point I think we're ready to plug in numbers if you like, okay? So we have the m chi c to the power 4, and that is equal to 1,322 squared. So this is 1,322 squared plus m squared for the lambda particle. The lambda has to be the lambda minus, that's 1,116 squared plus 1,116 squared minus the meson mass squared, the meson, the pion minus squared, that's what that is. So it's 139.6 squared divided by 2 times the mass of the pion, which is 1,322, minus 1,116. Yeah, minus 1,000, this number, minus 1,116. Okay, mega electron volt. So plug in all of the numbers and you should find an answer for the energy. Okay. Do the same analysis. Basically, instead of moving, where was the equation? Instead of moving the mass of the lambda, the energy for the lambda particle must move the mass for the pi particle on the other side, then do the same algebra as before. So follow the similar steps. So basically, instead of moving this is actually E lambda. So instead of moving E lambda, leave E lambda on this side and move E pi to the other side. You're going to have a negative in here. You square it. You're going to plug in the value of E pi, and you're going to find the value for E pi. That is basically similar to this one, except at the end you're going to subtract the rest mass of the pi particle. So the kinetic energy then for the pi particle in here, if I'm careful enough, so it's going to be similarly the mass of the chi particle, okay, squared of course, minus the mass of, or plus actually the mass of the pi particle now, because it was plus the mass of the lambda particle. So I'm using the symmetry in here, minus the mass of the lambda particle. So I switch these two terms because if it works for one, it works for the other by symmetry. Divided by, again, this has to be the same thing, mass of the chi times c squared, minus the mass of the pion c squared. Okay, make sure that the masses are correct. Again, this is 1322 squared. This is 139.6 squared. This is 1116 squared. This is 1322 squared. And this is 139.6. So if you plug in all of the numbers, you're going to find the correct answer. So I leave it to you guys to finish that and find the proportion from the total mass, okay? From the total energy. So which one carries the most of the energy? Typically, the lighter of the two particles, namely the pion in this case, will carry most of the kinetic energy versus the heavier, the more massive. Remember, the mass of this one is 139.6, whereas the mass of the other one is 1116, so it's about 10 times bigger. So I expect now the contribution or most of the kinetic energy to go to the pion. I need you to check these numbers, okay? I need you to plug in the numbers in here and verify that this is indeed true, the case in here. Okay. Problem 49. It's similar to the previous problem, except the starting point in here for this problem is a little bit different. So it says a particle moving in the x direction with kinetic energy 180 mega electron volts. Decays, so we have a sigma minus particle. So if I look at it's a baryon with energy 1100 and rest mass, that is 1197. Okay, so it has momentum already since it was moving in the x direction. Okay. And then it decays into two particles, basically a pion with a negative charge in it, a negative pion, and a neutron. So basically you have and a neutron. Okay. The pion the pion moves in the positive x direction, the y direction. So this is not correct. Wait a minute. The pion moves in the positive y direction. Okay. So this is not correct, okay? So what we have in here, so the incoming particle in this case was a sigma minus particle. Okay, so this is what happened in this case. So the pion moves this way. So now you need to have the neutron move in this direction somewhere so that its x component will be equal to the x momentum of this particle. And its y momentum needs to be exactly equal to that of the negative of the pion particle. So that's all there is to it. And after that, you're in business, okay? And we have the kinetic energy for this particle that we started with is 180 mega electron volts. Okay. And what else do we know? Okay, the sigma minus particle has a rest mass of 1197 mega electron volts. And we also have that of the pi minus, which is 139.6. I'm looking at table 44.3, by the way. And for the neutron, it's 939.6. mega electron volts. So we have all of the rest masses of the particles from the table, and the question is, what is the kinetic energy of the neutron, and what is the direction of its velocity? Namely, we have to find the Vy and the Vx for it, and it's going to make some direction or some angle with respect to the x-axis. Use the expressions for this ones in here. Okay, so let's see how we're going to proceed with this one. Again, the sum of the momenta is equal to 0. Okay. And so in we're going to use the conservation of energy, and the conservation of energy in this case is that of the, since we're given the difference between the kinetic energy and the rest energy for the the total energy and the rest energy of the sigma particle, so we can find basically its momentum. Okay, and we should be able to equate the y component of the momentum of the neutron to that of the pion, and the x component to that of the sigma particle when it came in. From here we're going to find an expression for both of them, and we're going to use the conservation of energy to find the energy of the neutron. And then at the end, since we were able to find the x component and the y component, we just divide the two of them and find the arc tangent of the ratio of the components, or use actually the x component over the y component, and from here we're going to find the conservation of the direction with respect to the x-axis, namely the theta. Okay, so I'm gonna because right now the recording is getting a little longer than what I was hoping to have. Okay, if you guys have difficulty with it, please let me know, and I'm going to give you a printed version of the solution. Okay. Problem 50 is identical to this problem. Okay, problem 50 is actually gives you a Chiron 0, basically neutral Chiron. Meson has a rest mass of 497.9. Actually, it's what is the? It's not even listed in the table. Yeah, but they gave you the rest mass for it. It's fine. K. Neutral meson moving in the x direction with kinetic energy. So they gave us the kinetic energy and we know the rest mass, so we should be able to find the momentum. Decays into a pi plus and a pi minus, which move off at equal angle above and below the x-axis. So basically that means their y components cancel out because of the fact of the symmetry, and the x component, which is just a double of either, must be equal to that of the incoming particle. Calculate the kinetic energy of the pi plus and the angle at which they make, use relativistic corrections. Again, this is identical to the previous problem, with the exception that now we're given the kinetic energy, we're given the rest mass, and the particle is moving in the x direction, but the outgoing particles, they're actually coming into at an angle in here. Again, I'm going to leave it for you guys to continue the calculation here, and both particles, they must go by symmetry in the same direction, basically. I mean, in the same angle. Okay? So this angle and the other angle must be the same, otherwise you will have an imbalance in terms of momentum in the y direction, because they have the same mass. The pi plus and the pi minus have exactly identical masses, so they cannot have the imbalance in terms of their momentum with respect to the y-axis. So again, I'm going to leave it for you guys. If you have difficulty with this problem, I'll be more than happy to provide you with a solution to these problems, at least, and post it on Canvas. We probably are going to meet this coming week to discuss the exam and the exam review that we need to do for before the last exam, before the final. Thank you. I really didn't want it to go 45 minutes, but it did. Thank you.